Thank you very much. I'm Geoffrey Fox. My work is in the Digital Science Center, where we have David already mentioned his work. I won't discuss it again. Judy and Gregor. And so we work in a slightly different fashion. We're mainly looking at applications, X informatics, with various values of X. And those include these areas here: biology, computational finance, network science. Phil discussed some of that. Biomolecular simulations, trying to understand funny results in the visualization of that. Remote sensing. Actually, David mentioned that, the analysis of data from ice sheets. And here we also work other computer vision problems with David. We have a work on pathology images and robot data. And we build algorithms and software for that. And as we like to do large problems, because we do big data, we try to make our algorithms run very well in parallel. And we try to run them on quite large machines and build software to support that. And the four areas we work on are deep learning, clustering, dimension reduction, and the image analysis David described. And we have lots of projects, most of which are with collaborators outside IU, some inside IU, and they vary from, say we have explicit one with Tennessee and Stanford, Andrew Ng's group there on deep learning technology. We have a large number of collaborators building this scalable data analytics library and so on. And let's continue. So we actually run very large computer systems, because we don't think the ones at the center of UITS work well enough for us. And currently we just added this 128 node machine, Haswell, which is roughly the latest Intel chip with a mix of 24 core and, in spite of what it says, 36 core nodes. And we also we work with SDSC, San Diego Supercomputer Center. They have a much larger Haswell system, 48,000 cores, and we build software for that. And we have a bunch of older machines. So these are not general purpose computers. They're aimed at doing two things: cloud computing and large-scale data analytics, and trying to see how the systems run. And we build technology to do so-called virtual clusters, which we believe is the future, the way to imagine things. So we have Python-based systems which support virtual clusters and dynamically create, say, deep learning environments or whatever you want on various different machines, varying from Amazon through these Haswell systems. So it takes out the variations of the underlying infrastructure. So work we do with David is on Internet of Things, and we support robots and drones and things controlled by the cloud, and we build the software that makes that work very efficiently. And we also take the algorithms and parallelize them to make them run much faster. And we're continuing that work in various ways. And the last slides are just some of the application work. Most people like stock, so here is work we're doing with people at UC Davis on trying to understand the structure of the stock market and how they vary. This basically takes the time series. We have 10-year data we're starting this with, and maps that to 3 dimensions and shows how that mapping varies as a function of time. This is work in progress, and it uses our multidimensional scaling technology, which is, I believe, the world's best, because it's parallelized and very robust. That same technology can be applied to biology. Here we have a so-called COG data set, which is a whole set of proteomics data, and it's mapped into 3D. It has this curious handbag shape when you map it to 3D, and then you can see what biologists think are clusters. And this points out one thing, that when people think they're clusters. They don't actually look like clusters when you project them and see how they're actually separated. That's an interesting feature of clusters, and we're essentially finished. This is the last slide, which is just being published. This uses the same technology on a much smaller data set of highly optimized fungi sequences, and it plots them in 3 dimensions. And most phylogenetic trees are done in effectively 1 dimension. This plots them to 3 dimensions, and you see a much better representation that this tree is a real tree and that these are distinct subdivisions of these fungi. Thank you.